Yeah. Sorry. Good morning. I'm going to start to talk about LNE sets, Lipschitz normal embed sets. Let me say some words before give a definition of that. In fact, if you think about by Lipschitz classification of analytic sets, for example, it's not an easy task, but it's easier to classify sets with respect to the inner distance, for example. If you want to classify sets under by Lipschitz maps, in fact, under inner by Lipschitz maps, it's a little bit, or no, a little bit, but it's easier to classify than if you want to classify with respect to the outer distance, for example. And the Lipschitz normal embedded sets apply an important rule here, because it's where the classifications are the same. So if you want to classify on the outer Lipschitz, on the outer metric and the other inner metric, for example, in this case, the classification is the same. And this is why I'm going to define what is an LNE set, okay? Definition. I think it's better to define before what is the inner metric. If I'm going to consider, for example, X in Rn, a path connected set. Okay. So we define, for example, if you take 2 points here, X and Y, in X, and if you now take an arc from 0, 1 to X, connecting X and Y, that means alpha of 0 is X, and alpha 1 of 1 is Y. So we can define what is the length of alpha has the following. In fact, if you now take a partition P of the intervals 0, 1, 0, 0, less than T1, etc., up to Tk equal to 1, we can define the length of alpha with respect to P to be the sum of alpha of T plus 1, no, T minus alpha of T minus 1, T I equal 1 to K, for example. And then we define the length of alpha to be the sup of all partitions P of L alpha P. In fact, this can be infinity, for example, okay? We say that a curve is H fiber when this number is a finite number, for example, okay? And then we define the inner distance of X between 2 points to be the infimum of all alpha connecting such that alpha 0 is X, alpha 1 is Y, of the length of alpha. So this gives distance, right? And this is what we call the inner distance of x, okay? So with that definition, we can define what means a Lipschitz normal embedded set, okay? X, we say that X in Rn is Lipschitz normally embedded set if there exists some constant c greater than 1 such that the inner distance of x is less than a constant times c minus x minus y, and for n x and y in x. And also you can say, here we can abbreviate this as ln e for short. And then we can say, for example, x is ln e at a point p if there is some neighborhood u contain x, p, sorry, such that x intersection with u is ln e, for example. So, sorry, I'm ln e. So we are dealing with local property. So for us, we are interested more interested in the condition of ln e at a point. Okay, but just to do a easy example, let me show, for example, the cusp is not ln e, just to get some insight of the definition. Okay, and then I will list some properties of this notion. Okay, so the set x given by I will show the real cusp is not ln e, and it will follow from what Alexandre will prove today in a easy way that the complex cusp is not ln e as well, for example. Okay. In fact, let me write here x squared, x cubed, for example. So the picture is more or less like that. We have this. So we can, for example, parameterize x as a we have in fact two parameterization of this. For example, we can parameterize this side of the cusp as maybe it's better to write in with other color. For example, here is x minus x 3/2, and here is x x 3/2. Or maybe this I will do it. So if you want, for example, to calculate the inner distance from a point x here, of this point to this point, For example, let me put only T. T is better. The inner distance to N and R connecting these 2 points have to go to the origin and then go to this point, for example. So the inner distance is at least this length more this length, for example. And this is more or less, of course, this is more or less, it's the same, has the same asymptotic behavior of T. So you can show, for example, let me call this, this point is AT, and this point is BT, for example, okay? So the inner distance of F of AT, BT is something like that, T, 2T more or less, okay? It's T. But if you calculate the outer distance from this point to this point, AT minus BT, this is 2, 3 half. And then you cannot put this is not true. This is C times 3.5, for example. For T is more enough. So you cannot find a constant C satisfying the definition. Okay? So X is not LNE. Let me say a property that guarantees that a curve in R2 is LNE, for example. If you have, for example, now, if now you have another example, if you now you have an analytic curve X in R2, for example, analytic, you can see, for example, this is the curve is something like that. I don't know what is, but there are many half branches of this, at least 2 half branches. Okay? And if you look now, the tangent cone of this guy, let me assume, for example, X is something like that. X is the union of half branches, gamma I, gamma 1, gamma 2, gamma k, for example, minus 1, gamma k, equal to 1 up to k, for example. K half branches. The intersection of each branch is only the origin, for example. I'm assuming that, okay? So how we can decide this guy is LNE or not, for example. And our way to decide is just looking at the tangent cone. For example, if you look the tangent cone now of this guy, of X, at 0, this is some union of half lines, because it's a cone of dimension 1, so we have only a finite number of lines. Let me call this J from 1 to some R, some lines. So X, so with that assumption, X is LNE at 0, if and only if K is equal to R, for example. It's an easy exercise to do that. I think you can do. Okay. It's more or less easy. Any half branch here, gamma I, has tangent cone half line. So we have, of course, always that R is less than or equal to K, for example. But when we have the equality, we don't have two half branches with the same tangent cone, for example. And this implies we have some from the lecture of Alexandre Fernandes. If this number, you have this number equality here, the contact between two of them is 1. So we can put some cone contain each branch that the intersection of each cone is only the origin, for example. So from this you can prove, for example, this. The X is LNE when you have K equals to R. So this is more or less the motivation. For example, in fact, we have more or less the same kind of result to the complex case for curves in the complex case. That means in fact, the complex case is a little bit more complicated, but in fact, no, a little bit more complicated, but it's a little bit different. In fact, in the complex case, also we have the number of, now is not branches in half branch, but we are taking in account branches, irreducible components of the curve. Okay. And if a curve is LNE, any irreducible component is smooth, and they are transversal. So you can prove, for example, a curve is LNE, complex curve is LNE, if and only if each irreducible curve is smooth, and the tangent cone has the same number of line, has the curve, has the number of irreducible components of the curve. And this was the motivation to the conjecture of Neumann-Pichon. Neumann-Pichon conjectured the following. It was a conjecture. X in Cn complex analytic set. Let be a complex set. So if X is LNE at 0, for example, then the tangent cone, so Cx is LNE as well. Now, a cone is LNE at the origin. If a cone is LNE at the origin, the cone is LNE globally. So LNE and is reducible and reducible. Reducible. That means reducible here means when you look, for example, when you look, as I said in the last lecture, the tangent cone here is given by the zero set of all initial parts of f, such that f is in the ideal of x at 0, for example. So this is an ideal. I will call this E star of x, for example. And then we have, for example, n over E star. of X. And then if the set is LNE, reducible, that means that there's no zero divisor of this guy that has no, the name is not reducible? Reduce it, yeah, sorry, reduce it, yeah. No, yeah, my fault, yeah, thank you. Reduce it, yeah. Yeah, sorry. So this guy is reduced. That means reduced here means this guy is reduced. So in other words, there is no zero divisors. Okay? So we are, no problem. No, it's, no zero divisors. No zero divisor means the guy is yeah, no, it's Newport. Yeah, I'm doing some confusion, maybe, I think. Yeah, the point is that this guy has no guy something like, it's not Newport. Yeah, yeah. It's new, yeah. It's Newport. Okay? Sorry. Yeah. I think I did some confusion with the names. But then I will not have time to prove all these things. But in fact, we answered this conjecture, Alexandre and me, Fernandez, and I in 2019. In fact, we proved even more than this. We could define a generalized notion of what means reduced here, even for subanalytic sets, and we could prove, for example, if X is a subanalytic set, and if X is a LNE set at 0, so the tangent cone is LNE and is reduced with that definition. That I will not define what means that, but I will prove what means. I will prove this part here. Okay. I don't have much time now. In fact, I would like to say some words about some properties, but you can read in the notes. I only say some other properties of LNE sets. For example, if you have a compact set which is locally LNE, that means which is LNE at each of point of it. So the set is LNE. Of course, NC1 submanifold is locally LNE. So NC compact C1 submanifold is LNE globally. Okay. LNE is a by Lipschitz invariant. That means if you have two guys, X and Y, by Lipschitz homeomorphic, so X is LNE if and only if Y is LNE, for example. Okay. So you can see this in the notes. So I will state what I will prove now. I will only prove in the case, our proof even works for sets which are not closed, for example, but I will state in the closed version of it. Let X in Rn be a closed subanalytic set. Closed subanalytic set. So if x is ln e at 0, then the tangent cone is ln e at 0. In fact, we can find also, in fact, this conjecture was a equivalence. X was ln e if and only if the tangent cone is ln e and reduce it. But we can find also a counterexample. You can find a counterexample in the notes, for example. Okay. Let me erase here. So I will start, for example, by proving if you have now two points x and y in the tangent cone x, such that x, I want to find now a constant c greater than 1, such that the distance of the tangent cone is less than c times this guy, right? So I will start by proving that means, and this distance, this c does not depend of does not depend of x and y. Okay, so I'm going to prove this when x, firstly, when x and y are in the sphere, the unity sphere. Okay. If I can do that, it's an easy task to prove in general for any x and y in the tangent cone. So since x and y are in the tangent cone, there are sequence xn and yn, for example, in the tangent cone, in x minus 0, and a sequence t in 0 plus infinity, such that xn over tn goes to x, and yn over tn goes to y, for example. And now, since x is closed, for each x and yn, there is some alpha n from 0 to 1 goes to x, such that alpha n of x of 0 is xn, and alpha n of 1 is yn, and moreover, the distance of x between x and yn is just the length of alpha n. Okay, and by assumption, we are assuming that x is ln e, so there is some constant, let me say lambda, so that this is less than yn, xn minus yn, for example. Okay, and I know this when you divide, for example, by tn, this goes to x minus y, for example. So if you divide by tn here, this is a bounded sequence, for example. So we can in fact define, for example, beta n to be alpha n over tn, another curve, and maybe I only know, for example, the length. This implies, for example, the length of beta n is the length, it's easy to prove, over tn, And of course, this less than lambda xn minus Tn over Tn. But I know this converges, so this is bounded, for example. Okay, so we know this is bounded. And if a arc has finite length, we can reparameterize this guy to be a one Lipschitz arc, for example. So we can, let me call, for example, this Ln, for example. And we can now define beta in tilde. In fact, we can, let me call this in this for one moment. Up to Ln to x, the reparameterization by the length arc of this beta n, for example. So this guy is one Lipschitz. And of course, beta n of 0 is is xn, and beta n of Ln is yn, for example. So you can, for example, increase a little bit more to. I think we can, for example, let this is bounded. For example, this sequence is bounded. Let me say Ln is less than L, for example, and we can define everything here from 0 to L, putting in this the following. This is we can assume, for example, from Ln to L, beta n is yn, is constant. So it's still Lipschitz, for example. The length is the same. Yeah. Sorry? Why beta is? Sorry, this is not in X in more. Sorry, yes, in Rn, right? Thank you. In Rn only. N is horrible, but let me put him here because sorry. No, it's not in X. Yeah. There's no way. No reason to stay there. So that I will define beta in tilde, for example, from L0 L to Rm, and now beta tilde is beta in tilde of t when t is here, and is yn when t is here. So since beta n is Lipschitz, beta n tilde is Lipschitz, beta n tilde is Lipschitz, for example, and the constant is 1. They are Lipschitz with constant 1, for example. So we have now a family of functions defined in the compact interval which are Lipschitz with the same constant. So we can use Haselas-Coll theorem, for example, to extract a subsequence of this, which is uniform convergent. Let me assume, for example, this guy converges to some, in an uniform way, some beta. And beta now is from 0 to L let me say some words why this is now in Xn, because every point here now, and when you fix, for example, some point t, and you put x and t here, this is something like tilde. This is something. If t, of course, is here, it's no problem. But it's here also. This is x and yn is a point of x. So we are putting, for example, this is a point of x. So I only wrote like z and j with t and j, where this point is a point of x. So this is converging to some point which is beta of t. So we are dividing a point of x by a positive number, and this is converging by definition to a tangent coin. This is why this guy is from here to the tangent coin. Okay. So I will prove now. We have something like that, because when you divide it, the length of beta and tilde is the same of the length of beta and tilde, which is the same of ln, for example. So so we can. It's an easy task, for example, to prove, for example, L beta is less than the limit sup of the beta and tildes, for example, but the limit sup is less than L, and we can prove now this is less than x minus y is a easy computation, for example. Just putting the limit here. The limit sup of these guys is greater than the length of the limit, the length of beta. But the limit sup of these guys is less than lambda times x minus y. This is why we have that. So we found, we proved this, in fact, because the length is greater than, this is greater than the inner distance of x between x and y, for example. So we have proved the theorem when x and y are in the unit sphere, for example. But now, let me assume, for example, of course, it's easy. The case 2, let me write like case 1. Case 2 is when x is a multiple of y from some s greater than or equal to 0. So we have a line connecting in the tangent cone there. So of course, if you have a line, it's easy. The tangent cone of the inner distance of x and y is just x minus y, which is of course less than lambda x minus y, because lambda is greater than or equal to 1, for example. In fact, we are going to prove, in fact, the constant c is lambda plus 1, for example. Lambda plus 1. Of course, if it's true for lambda, it's true for lambda plus 1. And then you can assume now the third one, x is different to s times y for n s, for example. So, and of course, we can assume, for example, change x by y. These guys are different because if they are equal, we can do the same to the x divided by the norm of x, and just now multiplying, it's easy. We found the same we find the same inequality when x and y. We could do everything more or less in the same way when x and y has the same norm. So we can even assume that. So in fact, we can assume, for example, here, this, by chain x and by y, okay? In this case, the picture is something like that. Just to finish. So you have the origin here. So we have y here, we have x here, for example. So we have something like that, and something like that as well. So this is the radius of that. So we have this angle here, this angle theta, for example. It's easy to see, for example, the angle theta is greater than pi over 2, right? Because here is when it's pi over 2, so theta is, in this case, theta is greater than pi over 2. So this guy is greater than this guy and this guy. This distance. This is just the distance. This is x, this is y, this is the distance x minus y. So you can, for example, write this to be y prime, which is x times y over norm over y. And I know, for example, by the first construction, we can compare these two guys. Here we can compare these two guys. So I want to compare the length of our geodesic here connecting x and y. Okay, let me. More 3 minutes. Okay. So the point is, of course, the inner distance of here to here is less than the inner distance of here to here and then of here to here. Okay? Let me call only D because it's hard to D over C of the tangent cone. The tangent cone of x to y is less than the tangent cone of x to y prime plus the tangent cone, the distance of y prime to y. But here we can connect by a line. And here we are in the same, in the case they have the same norm. So there is a constant, and this is lambda, in fact, x minus y prime, and this is y prime minus y. And this is, now I use the geometric interpretation here. This length is less than this, and this is less than this. So this is lambda less than x minus y, and this is x minus y, and then this is lambda plus 1 x minus y. And I've finished. Thank you very much for your attention. Okay. Do you have any question? You?
Does there exist a notion of ln at infinity?
Yep. Yeah.
This term is
yeah. It's, the notion is something like that. outside of a compact set. Outside of a compact set, this is LNE, for example. So we have some works about that recently, in fact. For example, we proved, for example, in the complex, so if you take a complex algebraic set, which is LNE at infinity, and the tangent cone at infinity is a plane, so the set must be a plane also. It's a very rigidity theorem. It's the complex structure is very rigid. Okay. Any other question? No? Okay, thank you.
Acho que essas são tuas.
Você quer ficar com ela?
Não, tenho aqui. Valeu. Obrigado. Morning, how are you? How are you? Okay. 2 minutes more? 2 minutes, yeah. The sound is, oh, okay. Good morning, everyone. So I'm going to start today with a special case. Actually, the general case of a special case discussed in the last exercise class by Professor Sampaio. Our last exercise class, Sampaio given a kind of definition of multiplicity in a special case. Then I will start today with the exactly definition of multiplicity that we will work with. Okay? So definition, proposition. For us, X is a complex analytic set, and we are supposed 0 is a singularity of X, okay? We are look X near 0, the origin. And dimension of X is equal to D, at least near the singular point, okay? So, then the proposition say that for any linear generic projection, pi to Cn to Cd, D here is the dimension of X. Generic for us means the kernel of the projection does not have tangent vectors to X at 0, okay? This intersection is just the null vector. Then, if you are in a setting like that, the picture is something like that. You decompose Cn, taking a Cn minus D, and Cd. Your set lives here. This is X. And we are supposing that in this vertical direction, there is no tangent vector to X at 0, okay? This is the direction, the vertical direction is the direction of the kernel of pi. This is the situation. So, if you are in this setting, then exists open neighborhoods of 0 here, U, and open neighborhood of the projection of the singular point, which is 0 here. Have an open neighborhood here, V. And this is A and B and sigma, analytic subset of CD, subset of codimension greater than 0. Codimension at least 1, such that this guy lives downstairs. This guy lives here, sigma, such that when you remove this guy and this pre-image of this guy on X, you have a finite mapper, a kind of covering, such that the restriction of my projection to X intersection this neighborhood, remove the pre-image of this ramification locus over V, remove this ramification locus, is a finite mapping mapping. I mean, finite is a covering with finite sheet of degree m. And moreover, m does not depend on pi, if pi is generic. This is what I mean by multiplicity. Even when x is not pure dimension, we will call this number multiplicity, okay? When this x is pure dimension, this number coincides with the Hilbert-Samuel multiplicity defined in commutative algebra. Okay, I denote this number by what Edison solved, is exercise solved by Professor Edison, was when x is pure dimension, at least near 0, then 0 is a regular point of x if and only if this multiplicity is equal to 1. This was exactly the exercise proposed by Edison. So, example. Once again, let's consider the cusp, the complex cusp. X, y, if you want to C2, such that x squared equal to x cubed. This is the real picture, but we are considering the complex one, okay? There is no picture, but let's think this is a picture of this set. Then we saw in the classes, in the lecture of tangent cones, that the tangent cone of x at the origin is given by the zero set of this form here. Then is y equal to 0. Y equal to 0 is this line. Y equal to 0 is the tangent cone. So if you take this projection, y C2 to C, and you take x and y, you project on x. This is generic in that sense. Why there is no vertical vector tangent to my set. This is generic. Then, in order to compute the multiplicity, you have to take a generic point here and compute the number of elements in the preimage of this guy on x. Image of this guy. This restriction to x. Then take a point here, t, and compute this. You have to solve this equation. Then this equation have two solutions. Then this guy have two guys here. Then our multiplicity is equal to 2. And this is a way to prove this point here is not regular. This is a singular point. In our first class, you work with the real cusp, and you prove that the 0 is a singular point. Take the tangent cone. The tangent cone was a half line. Here, the tangent cone is a linear subspace, and there is no corner in our sense. Then it's not possible to prove this guy is singular using the tangent cone is not a subspace. Okay? Then you use multiplicity, this characterization, for instance. So this is a very important number. as we see here, is a kind of way to measure how singular is your point in your site. Okay? Then our idea was to see all the geometric nature of, more precisely, is this number an invariant of by-Lipschitz mappings or not? So this is a north to think, okay? And we start to think about such a number. Then you have to introduce some definitions. Is it okay? Any questions? No. No questions. Let's recall the spherical blow-up. Of Rm at 0. Okay. Here we have Rm, and this is the origin. Then the idea is to take an explosion here to transform 0, a sphere, and in direction goes to the same direction. Now this direction ends on the sphere, not in the point. If you have a direction here, this direction ends here, okay? So then, suppose you have a singular set, a set with singularity at this guy, x. This is it, your x. When you do this spherical blow up, we have a lot of direction here. Let me draw. And these sheets, when you transform these sheets, they are diffeomorphic to the transformed of those sheets are diffeomorphic to them, and they disappear along a line like that. Okay. X prime. This is the idea of the spherical blow up. And the exactly formula of this guy is that it was defined by Professor Sampaio. Take a point in the sphere and a radius, and just go to that. Okay. So let me denote something here. What is x prime? X prime for us, you take the preimage of x minus the singular point. You remove the singular point, then you have a copy of this guy upstairs. Then you take the closure. When you take the closure, you put this kind of spine here. You add this spine. This spine we will denote by the boundary of this guy, the intersection. And as Professor Sampaio commented, that this guy is exactly the link of the tangent cone on the bottom of the board, on the exceptional divisor. This is exactly that, where this guy is the link of the tangent cone. Okay. This. So. Okay. So in our spherical blow-up, we have a kind of pamphlet here, pamphlet with a few pages, parts of our blow-up. Okay. And we will count the number of pages of this pamphlet. Let me precise what I mean by pamphlet. A point here, a point here, correspond to a direction which is tangent our set. When you put this point here, the corresponding point here is a direction tangent to our set. It's called simple. If there is an open neighborhood you have an open neighborhood here such that the intersection of my strict transform with this neighborhood, when you remove the exceptional divisor, is each connected component, component of this guy is a C1 manifold. Okay, in this neighborhood, we remove this spine. We will have finite many C1 manifolds, and when you add the spine X, let me exactly what I wrote here. Okay, and then for each of such connected component, a connected component of this guy, let's say A, you take one of them and you add this guy, A unit with the boundary intersection to A is a C1 manifold with boundary. Okay. When we remove this guy is a manifold. When you add, this is a manifold with boundary. This is what I mean by pamphlet. Okay? And one more thing, what is important, the dimension of this pamphlet is D, and D is the dimension of X near 0. This is a D-dimensional pamphlet. So then for each point here, you can define a number. But let's define a number. Define a number. KXV is the number of pages of the pamphlet. You have a point here. You have a pamphlet structure in this point. Then you count the number of pages. Actually, you have a theorem by Pavlutsky that when you are in the D-1 part of this guy, I mean, if you suppose this guy is subanalytic, X prime, X, then this guy comes subanalytic, then you can stratify. This is D-1 dimension. When you are in the D-1 stratum of this guy, the most of the points are simple. The set of simple points is dense there. Then take a point like that when you have this pamphlet structure and you compute this number. And of course, this number is locally constant because if you have a pamphlet structure here and you take a point near V, you have the same pamphlet structure, then you have the same number of pages. Then this number is defined on each connector for each connected component of the simple points set. Number depends only this connected component. So one more proposition definition. Proposition definition. So now we are in the complex setting, okay? Analytic. 0 belongs to X, and dimension of X is equal to D near 0 at least. So if X1, XR are the irreducible components of the tangent cone, this guy is analytic, this guy is an algebraic set. We already saw that with Professor Sampaio. Then you consider the corresponding reducible components. Take all of them. So then exists an analytic subset with dimension less than dimension of X. At least near 0. Such that when you remove this guy, each irreducible component intersects only one connected component of the simple point sets. Okay, let's say XY minus this analytic bed set intersects CY. CY is one of these good components in the tangent vector, the tangent cone. So then we define this number here as the number of pages of a pamphlet structure corresponding to this component. This is what I mean by relative multiplicity of x at 0 with respect to xy. Then we have the following formula. Multiplicity of x is equal to the sum of the multiplicity relativity times multiplicity of the reducible component of this guy. This is proved by Drapier. Yeah? Kudica and Rabi, né? Drapier, Kudica, Rabi formula. Okay? Then our goal was to prove that the multiplicity is by Lipschitz invariant. Actually, for dimension 1, multiplicity is by Lipschitz invariant. For dimension 2, is also by Lipschitz invariant. But for dimension greater than 2, we have counterexample multiplicity is not a by Lipschitz invariant. However, the relativity multiplicities, this guy are by Lipschitz invariant. This is the next theorem. And if I have time, I will prove this theorem. Any question? No question. Let me show how this multiplicity appear when you are in a hypersurface. Suppose you have a hypersurface in Cn. This is defined by a function, and the origin is a singular point of this set. Then you take the Taylor development of this guy. When these are homogeneous forms, and this is different to 0, then M comes with the multiplicity as we defined it. And when you take the factorization of this homogeneous form, we have also homogeneous factors, and have some powers here. The zeros of these homogeneous factors are our irreducible components of the tangent cone. So, right bigger? Okay. Here. Then Fm, you decompose Fm in this way. Huh? Okay. Thank you. G, Gr, then xy equal to 0. This is the irreducible components of the tangent cone, and these powers are exactly the relative multiplicity that I defined before. Okay, then when you compute this multiplicity, what is the degree of this guy? The degree of this guy is this times the degree of this times the degree of this. This is the Drapier, Kudica, Rabi formula. Okay, so The theorem is by Lipschitz invariance of the relative it was proved by CIMPA and I in 2016. 2016. So let me precise what I mean by Lipschitz invariant of this. Lipschitz invariance of this guy. So let X be analytic subset so actually Y B set that 0 belongs to X, 0 belongs to Y, and they have the same dimension near the origin. Let's say D. Let X1, XR, and Y1, YS be the irreducible components of the tangent cone of X and the tangent cone of Y, respectively. If X0 is lipomorphic to Y0, then R equal to S. The tangent cone of X and the tangent cone of Y has the same number of irreducible components. There exists a bijection permutation such that the relative multiplicity of X in XY is equal to the relative multiplicity of Y X sigma Y. This is the theorem. If I have time, I will prove this theorem, but I'm not sure I have time. Let me do an application of this guy. We do the following question. Is there any algebraic or analytic set which is a graph of a Lipschitz function, at least locally? A genuine graph of a Lipschitz function is the graph of the absolute value function. It's a graph like that. This is the genuine one. And the question is there any analytic set which is a graph of a Lipschitz function, at least locally? There is this, the smooth one. So if the guy is smooth, it is locally a graph of a smooth function, and a smooth function is also Lipschitz because you are locally. So the answer of my question is this is the only one example you can give me. If you are a graph of a Lipschitz function locally, then you have to be smooth. This is the application of this theorem. Let me state the theorem. 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 Português. Lipschitz regularity theorem. X RM analytic and dimension of X equal to D near 0. If X0 is lipomorphic to a smooth term, CD, then 0 is a regular point of X. So let me say some words about this theorem. This theorem was first proved by Birbraí, Ledoutrang, Sampaio, and I, with another hypothesis here. We suppose the lipomorphism had more regularity than just Lipschitz regularity. We suppose the lipomorphism and subanalytic map. And you arrive in this conclusion. Then, after a year, Sampaio removed this additional regularity and arrived in this version of the result. I mean, this is 2000. Then it comes from the invariance of the relative multiplicity in this way. Proof of the regularity Lipschitz regularity theorem. If you have a lipomorphism between these guys, then by the derivative of 8, Sampaio shows that there exists a derivative of this function. Is a bi-Lipschitz map between the tangent cone of our set to the tangent cone of the plane. But the tangent cone of the linear subspace is this linear subspace itself, huh? And this is Lipel, implies this is Lipel in particular. This guy is a complex cone. It is always a complex cone in the sense that this guy is algebraic set, and this is union of complex lines. This is homogeneous. It's a complex cone, and by that, this guy is a topological manifold. because it is homomorphic to a CD. Then it's a topological manifold. Then there is a theorem by David Prill, 1916. David Prill, that says if you have a complex cone, which is a topological manifold, then this cone must be a linear subspace. Then this guy is a linear subspace. Linear complex C linear complex subspace. Then let me compute the multiplicity of X. Let me compute the multiplicity of X. The multiplicity of X is equal to the sum of 1 to R of the relative multiplicity of R, multiplicity of the irreducible components of the tangent cone. But we have a bijection between this cone to this cone. How many reducible components are here? Only one. Then you have only one here. And what is the multiplicity of this irreducible component? Is 1. This is 1. Yeah? What is the multiplicity, relative multiplicity of this guy? Is 1. This is 1. Then the multiplicity of my set is 1. And by exercise solved by Professor Sampaio, 0 is a smooth point of X. Then I stop here. Questions?
In the real case, there is also a formula, Kurdi-Karabi formula for the density.
Sorry, can you repeat, please?
In the real case, subanalytic case,
Subanalytic case, yes.
there is also a Kurdi-Karabi formula.
Yeah.
And are these coefficients also by Lipschitz invariant?
The relative multiplicity, this. These are by Lipschitz invariant, yeah.
Ah, okay, good.
Yeah.
So you said in the complex analytic case, you had examples in dimension 3 and greater where the sets were by Lipschitz, but multiplicities were different.
Yeah.
Can that happen in a family? Supposing I have a family of three-dimensional sets where the whole family is by Lipschitz equisingular, is it possible for the multiplicity just to jump?
No.
Okay.
So there is a theorem by George Comte that guarantees that if you are in a family, then the multiplicity should be the same. By Lipschitz trivial family.
So otherwise we'd be in trouble. The other question I had was, I am interested in the complex analytic case, and in particular, I am interested in the Oriel.
And sorry.
In the Oriel.
Oh.
Yeah. So, if you have, for example, if you have a complex analytic surface, and the tangent cone is two-dimensional, but there are also exceptional lines in there. And what's exceptional about these lines is that every hyperplane that contains one of them is a limiting tangent hyperplane. So is there any hope about showing that if you have that if two sets are lipiomorphic, so we know that the tangent cones are lipiomorphic, that we preserve the Oriel?
Yeah. I mentioned something like that with Edison yesterday. Just, but we need some help to do this. Can you prove that if you have tangent lines, at least for surface, if you have exceptional lines, then you have some non-trivial loops in the link of the set?
Pichon did. You had the feeling that if you look at these exceptional lines and they are reflected in a tightly curled region in the space, and that somehow the fact that it's tightly curled should mean that it should be detected by the Lipschitz geometry of the thing. At least that's the intuition.
That's a very nice question.
Yeah, no, that's the question.
Thank you. Thank you. So,
Any other question?
no.
So let's thanks again.
Thank you.
Can everyone hear me? Trying to find out. Let me upload my file again.
Welcome back, everyone, in this morning session. It is a pleasure to now have with us yeah, that was an echo. So it is a pleasure to have with us today Professor James Damon from the University of North Carolina, Chapel Hill. And he will give a part of our course on determinantal singularities. And he's one of the people who have, I think it's safe to say, overseen this development over several decades. And that's so it's a pleasure to have him here. Welcome.
Thank you very much, Matthias. I'm trying to upload my Beamer file. I don't know whether it should be appearing, but I haven't seen it yet. Is there a way to check this? I've done it according to what Paulo said, and I'll try it one more time. Here it is.
All right, let me say, in the worst case, I think you sent me your slides already. Maybe in the worst case, we can try to.
Well, here's
forward
something
them
here
here.
now. It started to show something, and then it disappeared. I don't know whether if Paulo's there, he can. Okay. What's going on here? I figured as much.
Jim, can you hear me?
I can hear somebody. Who am I speaking to?
Yeah. And what's the name of your presentation?
Well, I did some revisions on it last night, so I have the file here.
You can share this with me now?
Yes, I tried to do that. Okay, let me do it again. I'm doing exactly what you told me. To go to my computer using share. I'm uploading the file again.
Yeah.
Okay, I'll do it one more time here.
What's the name of your presentation? Because we have two.
I said I revised this last night, so you don't have the latest version.
Okay.
That's why I'm doing what you explained to me to do.
You can go to the share.
That's what I've done.
Yeah.
I went to share. I went to my computer. I
Yeah.
did the upload, and I don't know what's happening here.
To see how we can solve this problem. Sorry.
You do this? You found in your.
Yes, I did. I've done it like 5 times now. I click the share button. I go to slides. I go down to add a file from the computer, upload file, and I go to the file which I'm using, which I kind of did a little bit of work on last night, this one, and I clicked on it. And I mean, when you did it with me before, it started processing and nothing is happening now.
You can send me for this in an email. I can do this for you here. I will share my email in the private chat. We can there to what we talking here is in transmission. Our audio is in transmission in YouTube now, because we have to talk to write this in the private chat. Do you found it? The private chat in the
I
right
do,
side?
but I don't know how to write to you in the private chat.
But don't arrive nothing you're writing here to me.
Okay. All right. So what are we going to do? I was afraid this was going to happen when we did this yesterday.
And
I did exactly what you told me from yesterday, except it's not processing now.
you can read what I send to you.
Yeah.
Can you send me your presentation this email when I share with you?
All right. Okay.
I will put this in your transmission now.
All right. Let me do this.
He sent me a presentation. I will share this.
I sent it just now.
You have?
I just sent it.
Okay, I will do this there.
I can try to go as he speaks.
Yeah, that's one second, please. Okay. Yeah. Yeah, I will put the here. You help him changing the presentation.
I will do my best.
Okay, thanks. Jim,
Yes.
we will share your presentation with the Matthias help.
All right. Okay. Now, how do I control changing the page of it?
I can change your presentation from here. These are the files you sent yesterday. I hope it's up to date.
No, I just
keys.
sent this morning. I just sent it this morning to Paulo. I did some revisions on it last night.
I can put this here. Wait a minute, please.
Okay. Do I have any? I don't have any control over the things.
Jim, if you like, I can try to forward the slides as you speak. and
Um,
hopefully Corey.
all right, this is going to be a curious event, let me tell you.
I'm sorry, but we can. I will try my best.
All right, okay. All right. Well, let me get started then. This is sort of famous words. Murphy's Law rules supreme when it comes to using computers, I guess. First of all, I'm very happy to be here. I'm sorry that I'm sort of the outlier who is only giving a talk online. I've just lost the screen again, so I can't see. Here we are. Okay. All right. Anyway, I'm happy to be here. No, go back. I'm still talking. Yeah. This is not going to work well. It's not going to work at all. Okay. So let me just say, to begin with, Maria and Terry have already given some talks on what do you call determinantal singularities. And they mainly concentrated on the case of M by N matrices where M and N are, could be different. And what, this is not going to work at all. I'm not sure we can do this, guys, to be honest. I just don't have any control over how this goes. And it's just too hard for Matthias to follow my train of thought, I think. I'm not sure we can do this. Can we, I don't know, maybe just stop this and just have an open period for people, and I'll just skip this because I just don't see how this can work, to be honest. Paulo or someone can talk. Hmm. This is my question.
Hello, Jim. Can you hear me?
Hey, yes, I can hear you, Matthias.
So the suggestion is to have my my part of the lecture now, and yours in the slot of the exercise session this afternoon. Would that be okay with you?
What time would that be?
That should be after lunch break.
Right after lunch.
2:30.
At 2:30. Okay. Well, yeah, if we can ever get this thing working, yeah, I'd be happy to do it then.
Then we have some more time to settle the issues, the technical issues.
Okay. Yeah. And you can go ahead and give yours. Well, you don't have to jump right in, but with a short break for yourself, and then you can give yours since you would be giving it next anyway. Yeah. Okay. All right. So anyway, we'll somehow be in touch later this afternoon then about this to see whether this can work at all. Sorry that this is not working. I tried to follow exactly what Paulo told me to do, and it worked when we went through it yesterday, and it's not working at all now. The exact same thing.
Yeah, I guess that's life. We have to improvise.
I said this is Murphy's Law ruling supreme when it comes to using computers.
Right. But I think this will be a solution then for the time
Okay.
being.
All right. Good enough. Sorry. Okay. Be in touch later.
Yes.
Bye.
Goodbye.
Bye-bye.
You're welcome. Um,
Welcome back after this short break. Murphy's Law struck again. Let's see how we recover from that. So I will take over with the follow-up lecture for the moment, and we'll speak about the topology of determinantal singularities. The topology of determinantal singularities is particularly interesting because it's widely open what can happen if you smoothen a determinantal singularity. recall from the ISIS courses that if you smoothen an ISIS topologically, it's rather simple, the object that you get up to homotopy. You always have a bouquet of spheres of one dimension. For determinantal singularities, this is not known, and we will see some examples where different things happen. But I would like to start with a case which at first does not seem to be too interesting topologically, namely topology of isolated hypersurfaces. That means we have an object that we have well studied within the last 1.5 weeks, an isolated hypersurface singularity with the only extra ingredient that we can write the equation as the determinant of a matrix. This appeared, for instance, also in Dirk's lectures as examples of homoloidal projective surface hypersurfaces, I think. So then we will eventually move on to rational double points and triple points. This is also a classical topic in the theory of surface singularities, I think. And then in the second lecture by me, probably tomorrow, we will see a few other methods to tackle the vanishing topology in cases where you do not know what is going to happen. All right, so let's jump right in. This is to remind you of the geometric setting for determinantal singularities. And I think these are very useful pictures to have in mind for what follows. So how is a determinantal singularity set up? You have some space CP with P variables and a map A0 into the space of matrices here. And then in the space of matrices, the yellow thing stands for the generic determinantal variety, which are the matrices which are degenerate, which have an upper bound on their rank. Maybe we can take the presentation here a little down so that we can read the full notes. So, but I continue in the meantime. So this map A0 can have a rather complicated image, but what we require is that it's transverse to the canonical stratification of the generic determinantal variety of the origin. There we go. Thank you very much. So then the pre-image of the yellow thing, this is the this goes through the intersection with the image here. The pre-image of that yellow thing down here, it's the EIDS or IDS in case we really have isolated singularity. And then choosing a landscape for the space of deformations, in this case, it translates to, we consider those deformations of the red thing which are induced from unfoldings of this map. So we may unfold the map A0 to get AT, and then maybe the image has a different position, but we can still take the pre-image of the yellow generic determinantal variety and eventually find some smoothing or other deformation of the EIDS, of the red EIDS here. Good. And another slide to remind you that maybe not every unfolding of the map germ gives you a smoothing. If, for instance, you have the Whitney umbrella and the image of your map has so high dimension that you cannot move it away from the singular locus of the yellow thing, then you will necessarily inherit singularities in your pre-image. So keep that in mind. And let's jump right into determinantal hypersurfaces. By the way, when did I start? Let's say we started at 11, right? Is that safe? Okay. So consider the function f. This is well-known A2 singularity, right? And then we can, if we want, we can choose a matrix structure for that. And we've been occasionally discussing this already the last days. For instance, we could write f as the determinant of a 1-by-1 matrix, which is a rather boring matrix structure. We could also do this. write it as the determinant of this matrix, but then this is in a certain sense not minimal because we have this unit entry here. This is invertible, so we can apply row and column operations to reduce this to a diagonal matrix, where we have F up here. If you do the computations, you'll find out that's what's happening. F up here and 1 there. So effectively, this is again just 1 by 1 matrix. So a boring matrix structure again. Same holds for this. But we could also choose this matrix structure. Right? And there's some irreducibility in the sense that you cannot do anything reasonable to the matrix that will significantly simplify this matrix structure. Or what you could also do is take the first row here and add it to the second, or subtract it from the second. You get another matrix, but these should be equivalent in some sense. And if you have followed the last few lectures, then you probably know that this is the GL equivalence that Professor Ruas was talking about. So one natural question is, if you have a hypersurface singularity, how many different ways are there to write F as the determinant of a matrix, and up to which equivalence do you want to classify this? So let's see here, proceed with this example, because, well, there has been a classification by simple symmetric matrices and also by simple square matrices up to GL equivalence that has been done by Bruce and Tari. And there you have, you will see the lists, or I will show you one of the lists in a minute. And there you have different matrix structures of simple matrices in the category of GL equivalence. And they all turn out to have these ADE singularities as determinants. So there you have some candidates for how to write your ADE singularities, at least, as the determinant of a matrix. And I want to show you why the vanishing topology is even interesting even in this case, although you know it, what's happening. It's a bouquet of spheres in the smoothing. And the interesting part is hidden in the study of the discriminants and of the semi-universal unfoldings. So in this case, I think you have seen several times, even this week, what the semi-universal unfolding is. You take a monomial basis of the Milnor algebra and you perturb by the corresponding functions, 1 and x. And you introduce two unfolding parameters, u1 and u2. And then you get a map from C3 times C2 to C. And what you find then is a family with a two-dimensional base. And over different points, here you have different fibers. So of course, over the origin, you have the original singularity, which has a real picture like that. Then generically, you will have points here with smooth fibers that might look like this object up there. And you see a real shadow of the two spheres that are hidden in the complex domains. Here is another smooth fiber, which has a real picture that looks different, but of course you know that they are diffeomorphic in the complex in the complex setting. And you have a set of special points, namely the discriminant, where you have singularities. And in this case, here you have an A1 singularity in every fiber over this discriminant delta F. We have been computing these discriminants in the computational lectures. So let's compare this to the semi-universal unfolding of the matrix up to GL equivalence. We take the matrix and we do the computations of the extended tangent space that were presented on Monday, I think, or Tuesday. And we eventually find that the equivalent of the Milnor algebra is a space of monomials in matrices that we can perturb with. In this case, this is a semi-universal unfolding of the matrix A. And I introduced the parameters T1 and T2 for that. So we get a similar picture. We get a two-dimensional base for the unfolding of the matrix. And then we can take the determinants of the fiber matrices, let's say, and see what kind of singularities or Milnor fibers we get. So original singularity as before, and smooth fibers over the generic points. Should look similar, at least in the complex setting. And then we have a matrix discriminant, which in this case consists of two branches. One's the T2 axis, and the other one is a parabola. And in both cases, you have singularities in the fiber. And then the natural question is, how are the unfoldings of F and the matrix related, right? So we can check this by hand in the example. That's something likable about examples. So we can take the matrix for the unfolding and just do the computations, right? We absorb the deformation parameters here, and we expand the determinant, so we eventually find F minus something involving the T coordinates. And then, since the unfolding capital F is semi-universal, we must find a way to pull the deformation back, right? The unfolding of the matrix has to map to the unfolding of the hypersurface so that everything pulls back from there. So we have to find this map from the T parameters to the U parameters, and probably some diffeomorphisms of C3, such that this relation holds, right? And you see what the problem is up here. The Milnor algebra of F had 1 and x as a k-base, as a monomial basis. But here we perturb by the x squared term. So how do we get rid of this? I think the spoiler has peeked up on the slides. Who knows? Tjernhouse transformation, right? So what you have to do is, to kill the x squared term, is substitute x by this new variable or this new function, and use this as the diffeomorphism here. And luckily I did the computations for you, because if I did them here by hand on the blackboard, I would certainly do a mistake. We would lose a lot of time. So you do the substitution, you already get complicated expressions, and then eventually you find this. So this plays the role of U2 and this of U1. And this is a perturbation in x and a constant term as before. Right? So from this, I thought it was still on this slide. From this, you get what the map theta should look like. It's rather complicated. So what happens? This is neither an embedding, nor is it a submersion or anything. It's a branched covering of degree 3. Why of degree 3? Well, take some random values that you want to have here. Here you can solve for T1. Substitute there. It's a degree 3 polynomial in T2. Right? So degree 3 branched covering. The discriminant for the matrix decomposes into two parts. Right? And these are the equations. This is the parabola and this is the axis. And they have a geometric meaning. They are characterized by this map AT being non-transverse to different strata. And there it helps to go back to the pictures that I showed in the beginning and try to find what this means. So another remark is that since the Milnor fiber of the hypersurface, by construction, it pulls back to the smoothing of the determinantal singularity, we know that the matrix discriminant has to be mapped to the discriminant of the hypersurface. And we can even check that by substituting in the equations. So even though the expressions here are very complicated, everything simplifies at times to give surprisingly simple equations again. So this is if you substitute the theta in this well-known equation for the discriminant of f, then here you find the decomposition into two components. And one of them has multiplicity 2, the parabola, and the other one has multiplicity 1. Okay, I can recommend to do this as an exercise, maybe for the dk singularities, for d4, d5 or something. You'd have to do it once to get a feeling of what's happening, and you will see that already here in the simple examples, it's really complicated to do everything by hand. So the question is this a coincidence that you have this branched covering and relation of discriminants, and which other parts of singularity does this singularity theory does this relate to? And the reason why I wanted to start with this example is that Goryunov and Tsakalyukin, they have observed a nice correspondence between choices of matrix structures and studies of this discriminant and the induced maps on the semi-universal unfoldings. So their observations were for simple symmetric matrices in two variables and their hypersurface singularities. And how does that go? Well, here is a list of the simple symmetric matrices, which were classified by Bruce, I think. And this is everything that can happen for this size of matrices up to GL equivalents, symmetric GL equivalents. And as you can see, when you take the determinant, you always get an ADE singularity. Interestingly, the E8 singularity does not appear here. So what's the next thing you can see? The GL codimension, which means the base, the dimension of the base of the semi-universal unfolding, it always coincides with the Milnor number of the hypersurface, right? K plus 2 is the Milnor number here of the determinant, and K plus 2 is the GL codimension. So you always have a chance to have a finite covering map for the comparison for the induced map on the semi-universal unfoldings. So what Goryunov and Tsakalyukin found is that there's more to this, right? So let me try to briefly describe you what's happening there and what the discussion in their paper is. So as you may know, I go through this very quickly because we don't have time for the whole history, but I try to summarize what you need to know roughly. So for every ADE singularity, you know that there's a corresponding Lie group. And this has a Lie algebra. And the Lie algebra has a so-called root system. So these are very technical things, and you have to remember a lot of details. But let's try to summarize what we need from this. So this is a finite set of non-zero vectors in a real vector space, in a Euclidean vector space, satisfying certain geometric properties and symmetries. And in fact, these well-known Dynkin diagrams, they encode these root systems with vertices corresponding to simple positive roots, they are called. So some of these guys, and edges according to the angle in which they of their relative positions. So for any root, you have a reflection, and I will show you this in a minute, right? You have an orthogonal hyperplane, and you can reflect on this mirror, right? You can mirror the whole real space. And then you can complexify this, which has the advantage that the algebra will be more simple. And you can generate, you can consider the subgroup which is generated by all these reflections. And because of the symmetry properties of the roots that I did not write down here, you will obtain a finite group of these reflections. And you call this the Weil group of G. And for any finite reflection group, it's a well-known theorem, but unfortunately I forgot the name. Maybe somebody can say this. If you have a finite reflection group, the quotient is again smooth. So you get a branch covering. So I tried to draw some pictures of our previous example to take you where we left off. So for the A2 singularity, you have R2 as the vector space for this Weyl group action. You can write down, you can find some set of simple positive roots, V1 and V2. And you already see that they are in a hexagonal or triangular relative position. So you have orthogonal hyperplanes, HV1 here and HV2 there. And if you start reflecting and build the whole kaleidoscope, then you will eventually find that there's one more reflection, which is the reflection at this hyperplane, which should be the composition of the first two reflections. And when you take the quotient of all these reflections, then there's one slice of pi which you can choose as a representative, as a set of representatives for the quotient. And you can choose it, and it's a Weyl chamber, and this is called a Weyl chamber. So as for the Dynkin diagrams, here you have chosen two simple positive roots, and according to this relative angle of 120 degrees, they are joined by the edge. So the Dynkin diagram looks rather simple, but you could have also chosen this root, and if you put all of the simple roots together, then you get the so-called affine Dynkin diagram or extended Dynkin diagram. This will become important in a minute. So when you have this Weyl group, you could take one of the mirrors out, right? You have, in this case, two mirrors that generate the whole group. Now take out one mirror and say what's left. And you get a subgroup W tilde, W prime, right? And you can take the subgroup only, the quotient only with respect to this subgroup, right? Then this half will be reflected on the other half of the space. And you get a commutative diagram like that. So take the quotient with respect to the whole group and only the subgroup, and then eventually there will be a map complementing this. Why am I showing you this? Well, these two are precisely the pictures that we had in the discriminants. This is the discriminant of the hypersurface. This is the discriminant of the matrix. So this is not a coincidence. I need to give you one more fact from classical singularity theory. So if you have a simple hypersurface singularity, then the Milnor number is equal to the dimension of the vector space of this root system. And this quotient by the Weyl group can be identified with the basis of the universal unfolding. Unfortunately, I didn't find where this was proved, but it's mentioned in the old paper by Brieskorn on Springer resolutions, and you can also look it up or it's used in the paper by Goryunov and Sakalyukin, and maybe you can go down further in the references there. So it's not a surprise that these Weyl chambers and Weyl groups, they appear in the theory of unfoldings of ADE singularities. So what's the statement? We have the reflection hyperplanes of the roots, call them curly A, and then we have this quotient map, and in the image, these original mirrors, they are somehow folded and squeezed together, and then we get the discriminant as the image of the mirror constellation. And now the observation by Goryunov and Sakalyukin was the following. We have a one-to-one correspondence of pairs of Weyl groups, specific pairs of Weyl groups, and the correspondence between this and choices of matrix structures for the for the hypersurface singularities. So not all pairs of Weyl groups appear here, but they are related to certain operations on the Dynkin diagrams, which is either deleting two vertices of degree 1 for the 2x2 matrices, or deleting one vertex of degree 2 from the other, from the affine Dynkin diagram to get a 3x3 matrix structure. So without the, yeah, I think this is best illustrated in the with another picture. So here you have the affine Dynkin diagrams. I draw in purple what distinguishes them from the non-extended Dynkin diagrams. And then every vertex comes with a number, and well, you choose two vertices of degree 1 and you remove them. You have less hyperplanes at which you reflect, and then you get a subgroup of the Weyl group. And you can do these procedures here with every one of them. And then what happens is, to any choice of such a subgroup, you have a choice of a matrix structure. And if you only mod out by this W prime subgroup, you happen to get the discriminant of the matrix up to GL equivalence. And moreover, we have a biholomorphism of a decomposition of the discriminant. This discriminant now decomposes into two parts, which we also saw before, depending on how the image is non-transversal to the generic determinantal variety. And this corresponds to the subset of mirrors which are in W prime and those which do not belong to W prime. And moreover, here, if you take the quotient, the full quotient to this is the classical theorem, which is also in Brieskorn's paper, the full quotient to get the deformation space and discriminant of the hypersurface, and the partial quotient to take the discriminant of the matrix of up to GL equivalence, and this map that makes the diagram commutative. This turns out to be precisely the pullback map for the semi-universal unfoldings, the map theta that we saw in the beginning. So this is roughly a summary of what's happening there. So with the determinantal singularities, in this sense, you can take the ADE story and spin it further, right? You can take the Platonic solids and marvel about the natural beauty and symmetries. And you may all have heard how this is related to the ADE singularities and the Springer resolutions and so on. And this seems to take the story further, involving determinantal singularities. And I'm telling you this, or I decided to start with this, also a little extended, because there is a lot of young people who might be interested in things to look at and to go further. So, where are we heading? Yes, this is the extended table, the table from before, but extended to the results by Gorionov and Sakalyukin. So here you find the pairs of Weyl groups for the choices of matrix structure. So this matrix structure corresponds to that pair of Weyl groups, this one to that one, and so on. Good. So how was this theorem found? Well, actually, it was found by considering monodromy in the semi-universal deformations. And in order to make this monodromy locally non-trivial, you had to take a one-variable suspension of the curve singularity, because for the A1 curve singularity, there is no relevant monodromy. And at least for the 2x2 matrices, this can also be realized in another way, up to GL equivalence. You can establish a one-to-one correspondence of simple symmetric curve singularities and simple square surface singularities, where you take a symmetric matrix and you add this symmetry breaking part in a new variable. So For the 2x2 matrices, you could even say that this was not only about curves, but you can reinterpret the whole story for surfaces. For the 3x3s, it's more difficult because, or it doesn't work this way. And in particular, this correspondence, it identifies the unfoldings, the semi-universal unfoldings on both sides. Right? So let's look at the surfaces. This is now a modified list from the simple surface singularities, or the simple 2x2 matrices in 3 parameters by Bruce and Tari. And these are their original normal forms, and here in this other column I show you the some modified version so that you see how this symmetry breaking addition of the new variable comes into play, right? And if you delete the z from every of these entries, you should get more or less the corresponding curve. So what about surfaces? This is something that I want to throw to you as a maybe long-term exercise. So matrix forms and simple surfaces, where do they come together? This plays also a role in the Mackay correspondence. So Mackay correspondence, or one version of Mackay correspondence that I took from the Handbook of Singularities that recently appeared, should go like this. You take a minimal resolution of your ADE surface singularity, and then you can relate the vertices in the Dynkin diagram to the components of the exceptional divisor via the dual resolution graph. Right? You may have seen this or even take it as a definition of the Dynkin diagram, but otherwise look it up. And then on on the singularity, you have a finite set of maximal Cohen-Macaulay modules, M. These are vector bundles outside the origin. At the origin, something weird can happen. You can pull them back to the resolution, kill the torsion, and it turns out you get a real honest vector bundle, a complex honest vector bundle. You can take the Chern class and it will be non-trivial on exactly one component. So that's how you can relate a maximal Cohen-Macaulay module to a vertex in the Dynkin diagram. And then a maximal Cohen-Macaulay module also has a presentation matrix as a module over the ring over the power series ring. And it has to satisfy this property. The determinant of this presentation matrix has to be some power of F. So exercise, go there and see, is this really, again, the same correspondence that we find in Gorionov and Sakalyukin? I didn't have the time to look it up, but maybe we should look this up and see what's happening there. Right, so I expect that here, this should be more or less the cases where k is equal to 1, so that A is equal to F, and yeah, let's check this. Also for the decay singularities and so on. Good, so we want to go further. I spend a lot of time now on this, you could say, one paper, but as it turns out, it's an observation that has been made also by other people, or this contains a lot of observations that have been made by other people. And for surfaces, the story came from maybe a different angle. And let me jump into the surface theory by briefly recalling what a resolution in family is. So let this be a deformation of x0, some singularity x, over a parameter space B. We have seen this several times. And then I say that a resolution in family, or a partial resolution in family, is such a diagram. Well, the lower square is just the deformation written as a square. But then you have a part that sits on top of it and projects down with pi and the restriction of pi to the 0 fiber. And we require that this above this family on the top of the y's is also flat, and for every parameter t in the base, the projection on the fibers is either a resolution of singularities, or for what we need, maybe it's just some blow up, some partial resolution, right? But the essential thing is that whatever kind of blow up construction we have here, it can be done for the whole family at once. And then in every fiber we find what we want to find. So why is this important for surfaces? Because, as you may know, for the simple surface singularities, or in other people call them the rational double points, and they have probably 5 or 6 other names by which people refer to them. These simple singularities, they admit a resolution in family. That means topologically, it does not make a difference whether you take the Milnor fiber or you resolve by blow-ups. But they admit a resolution in family, not for the sim-universal deformation of the singularity, right? So in the lower square, you could hope that you can take the sim-universal deformation of your ADE singularity and then just put something on top straight away. This does not work. But what you have to do is a so-called Galois base change. And it's just another word for this branched covering that we saw in the early example. So this is known for surfaces, that such a resolution in family exists after Galois base change. And I'm not sure how much time we should really spend on this, but this is, again, can also be taken as an exercise that you can construct these resolutions in family for the AN singularities and the DK singularities, and probably also for E6 and E7, but not for E8, using the so-called Turina modification. And this has appeared in several papers, and one where the resolution of singularities is carried out using Turina modifications. You can ask Helge Möller-Pedersen here in the audience if you need assistance in solving this or following these parts of the course. So I want to tell you what the Turina modification is. And I'm afraid I have to do this pretty quickly. Yeah. So what happens, it's very technical. It's in a sense not very geometric, but you can I try to make it as geometric as possible. So let's start here. You have the generic determinantal variety of M by N matrices with a bound on the rank S. So on a Zariski open non-singular subset, the matrices have rank precisely S minus 1. So every matrix in here, to any matrix here, we can associate the subspace that is spanned by the image. Or alternatively, we could also take subspace which is given by the kernel, right? Let's take here the image. And this provides somehow a Gauss map to a Grassmannian, right? Or you could say generalized Gauss map. And you can take the blow up or the closure of the graph of this Gauss map phi, and then what you get is the Turina modification of the generic determinantal variety. And it turns out to be smooth, and you get the natural two extension maps, the projection down, which is an isomorphism outside the singular locus, and the extended map to the Grassmannian. And then what you can do is you can take the fiber product of this resolution of singularities here with any matrix that defines your determinantal singularity, and you get some other family up here, right? You can do this with even with an unfolding of a matrix singularity. And then you get here the so-called Turina modification in family. So here in this lower square, you have the natural, the natural deformation of the determinantal singularity, and then via this fiber product construction, you get an induced family for the Turina modifications. But be warned, this one up here is not necessarily well behaved. It's only well behaved in some particular cases. So at this point, I should maybe ask, how are we managing with the time now, with the special situations of this morning? Yes. But how long should I continue now? Should I fill up the slot? Or I don't know how we should. When would I stop usually? Okay. 12 is on the schedule. Ten to. All right. So, yes, I have material. Don't worry. So, Turina transformation in family. Let's go back to this one example. I mean, it should always be nice to have one example to the end. So, how do we write down the Turina transformation in family? We take the unfolding, and here these are the equations for this fiber product from the Turina transformation. So you introduce two homogeneous variables, A0 and A1, right? Generically, the matrix will have rank 1, so the image will be one-dimensional. The corresponding Grassmannian is just a P1, so rather simple. And you can take these equations for the Turina transformation in CA3 times P1. And then you find that the chart A1 is non-zero, it's always smooth. Why? Because if you put this equal to 1 and this equal to 1, then you see you can eventually solve for y and you can solve for x in both charts. So nothing happens in that chart. In the other one, there is still a singularity, which locally has this equation. And we can repeat this process, writing that singularity as a matrix singularity. We can choose a non-trivial matrix structure and then do the Turina transformation again. And this will introduce another necessary base change for the deformations. And yeah, we will see that in a minute again. So the Turina transformation of that A1 singularity is smooth. It has these equations here. You can check that it's smooth, and the base change necessary is that you do this T1 prime squared there, so that you can write the original deformation. Let's go back to the original deformation. Here, this equal to 1. You cannot absorb the T1 in the matrix, but if this was a T1 squared, it's okay, because then this matrix will do the job. Right? If you take the determinant, then you will eventually see determinant of A plus T1 prime squared. So what you end up is this Turina transformation in family, and then here is the original semi-universal unfolding of the hypersurface. You get one base change from the first choice of a matrix structure. You get the Tirana transform there. This has a singularity. You choose another matrix structure for that local singularity there. You get the other base change. You get a second Tirana transformation locally. And then here you have this tower, which up here is a full resolution in family over this base. But I suggest if you're interested to start working in this, you have to sit down and do everything yourself. Good, that's just what I said. And interestingly, this Tirana modification, the name comes from this paper by Tirina, and she has used it for the rational triple points first, right? So it's not natural to apply this in the ADE setting, but the rational triple points. So these are naturally matrix singularities. They are a special instance of this so-called Cohen-Macaulay codimension 2 singularities, and they turn out to coincide with the simple isolated Cohen-Macaulay codimension 2 singularities in C4, which is from a classification by Anne Frübes-Krüger and Alexander Neumann. Right? So this correspondence that you had for the ADE singularities, that the simple singularities are exactly the rational double points. It's extended by the simple Cohen-Macaulay codimension 2 singularities are exactly the rational triple points. And here I brought you one example for this. This is a matrix for a rational triple point. And you just plug in your favorite values for these integers L and K, and you get one of these rational triple points. And I said these Tirina transformations had been used to construct resolutions in family, so you can construct a resolution in family also here, and you can do the Tirina transform for that matrix, and you find out that in the transforms you have two local new singularities at the points 0 and infinity, and they are of the double point type, right? And for them, it's already known that resolution in family exists, and you can piece everything together, as in the previous example, to get a full resolution in family. That's where the Tirina transformation originally appeared. Good. And to finish with today's lecture, let me briefly summarize how this story goes on, also as an outline to you for what there is still out there to look at and to bring together. So for rational surfaces, we have a rather well-developed theory, and unfortunately, I'm not an expert, but you might find people here that know more about rational surfaces than me. So first thing, well, this is just to know. If a rational surface singularity has embedding dimension P, then, and it is determinantal, then it must be determinantal for a 2 by P minus 2 matrix, right? So a lot of these rational surface singularities are determinantal, but they have a very specific determinantal structure. And another result that relates the rational surfaces to determinantal singularities is this. If the rational surface singularity has embedding dimension P and it is determinantal, now it is determinantal if and only if this dual resolution graph has a very specific form. So if you have not seen this resolution graph before, it's the Dynkin diagrams of the ADE singularities. They are a special instance of these dual resolution graphs. And resolution in family and determinantal structures has also been used quite a lot in the theory for rational surfaces. For instance, Artin has shown that you may have several components in the base space of this semi-universal deformation. Recall from Pinkham's example that this might be the case, right? But there is, so there is always a smooth base space which parameterizes those deformations of a minimal resolution that blow down. And you can again get such a comparison map, and it takes this smooth parameter space surjectively onto one component, which is now called the Artin component of the deformation. So what we saw before in the very beginning example, here is another generalization of that. Right? There is a so-called Artin component, or there might be a so-called Artin component of the rational surface singularity, which is singled out by the case that after some pullback, you can write the deformations there as determinantal. No, not yet determinantal, as resolutions in family. And then Wall has shown that for a determinantal rational surface singularity, the Artin component consists precisely of the determinantal deformations, right? So this middle block was about resolutions in family, right? And Wall has shown that if you have a determinantal structure, then it's really the determinantal structures. And one consequence of this is that if you have a resolution in family for a rational surface, you only find the tree of P1s upstairs as an exceptional divisor. And then if the Milnor fiber is homeomorphic to that, then you see that in this case, you also have a bouquet of two-dimensional spheres as the Milnor fiber. Okay, and then tomorrow we will proceed by looking at some other examples where the topology can be rather wild. Already actually to this afternoon in the exercise sessions, I would like to show you the topology of Pinkham's example on both smoothing components, and you will see it can be very messy. So you're not always as lucky as here to have the two-dimensional spheres. And I think that's a good point to stop. Thank you. Questions? Yeah, let's deploy the microphones.
It's more a remark. First, thank you for this excellent overview of so many nice mathematical theories in 45 minutes. Each of them could serve as a mini course.
Yeah, that's a problem here.
Going back to this kind of linking diagram business, I have two references. The first one is the reference of Vladimir Arnold on matrices depending on parameters.
Yeah.
Which is quite elementary and shows also this map.
So this was Duncan diagrams of matrices?
No. The name is matrices depending on parameters.
Ah, yes. Okay.
And this shows that this map modulo de Waal group is related to the map of the eigenvalues of the matrix to the coefficients of the characteristic polynomial. Very easy to read. And the other is the book of Peter Slodowee.
Slodowee?
Yeah, simple singularities. And some dots and then Lie groups.
Okay.
The title is Some Words in Between. Okay.
Does this L go with that bar? I don't know.
No, it's just slowly.
Okay. Yeah, thank you for the references.
Yes, and Peter Slotherby was also a student from Bonn, and he wrote very nice things, but he died very young.
All right, thank you. Further questions or remarks? Yeah, Terry?
One thing I was thinking about during the first part of your talk is that there you're looking at a comparison between the base of the versatile deformation in the matrix case and that of the hypersurface that the determinant of that matrix gives you. And so there you have two finite dimensional bases.
Right.
Well, there are going to be cases where you have a finite dimensional base for the matrix case where you don't have a finite dimensional base for the determinant. As soon as you get into the non-isolated singularities, even if they're EIDS, that's going to happen. So I'm really curious, what is this going to say about about all possible deformations of the determinant? Because this comes up even in square matrices, right? So
Yeah, I think this is a square matrix phenomenon. And I was thinking a little bit of, the first one of the junior talks yesterday. There was mentioned some technique by Bobadilla and others that you don't want to, you have a restricted set of allowable deformations of the origin, and then maybe if you keep the singularities of the origin, you get a different deformation theory and again a finite map, but that has to be looked at. I don't know. And I think Jim Damon, he will also talk about non-isolated hypersurface singularities in the determinantal context. So we can pick up on that question there, probably. Good. Further questions, remarks? No? All right. Then thank you for your patience. See you in the afternoon.
So just a quick inform. As you know, the lecture of Dean was postponed for after lunch, right? And for now, there is no activity. Okay, everyone is free to for lunch and so on. And what else? Mais alguma coisa de questão, né? Okay, that's it. Thanks a lot.